Welcome back to this session. We'll have two talks in this session by Abhishodh and Vijay Agarwala. So first talk will be by Abhishodh on deconfined quantum criticality without the quantum.
I'd like to begin by thanking the organizers of this wonderful conference and for the opportunity to present some of my results. So the title of my talk is Deconfined Quantum Criticality sans Quantum. In fact, it's also sans deconfined, so it's merely critical. I'll explain what all these words mean. A better title is Classical Origins of Random Incompatible Transitions. This is these are results based on a recent preprint I put out with Nick Jones at the University of Oxford. So this talk is largely going to be about certain aspects of spontaneous symmetry breaking. So I'll begin with hopefully an entertaining slide about spontaneous symmetry breaking and how one can and its importance in condensed matter. So a quick recap is in physics we're interested in some problem P for which we want solutions S. And typically our problem comes with a collection of invariances which are the symmetries of the problem. Now the question we're interested in is what happens to the solutions? Like, do the solutions also have all the symmetries of the problem or not? So typically it turns out to be not the case. So let me show a short video of how symmetry is spontaneously broken in the way that I just described. So it's a bit choppy because it's shared over Zoom. So what you see here is a wire frame in the shape of a cube. And the cube has the symmetries of a cube. If you dip it in a soap solution, what this tries to do is the soap tries to form a film of minimal area. But you can see that the solution, which is the minimal area minimizing soap surface, does not have all the symmetries of the cube. There's this little square in the center that can point, that is chosen a particular direction to point at. So now this could point in any of the three directions. And what you find is there are actually three solutions to this area minimizing problem. And this is typically what happens when symmetry is spontaneously broken. When the solutions don't have the same symmetries as the problem, there is a lower bound in the number of solutions that are possible, which is obtained by dividing the number of symmetries of the problem by the number of symmetries of the solution. So in the video that I showed, the system has three solutions, which tells you which demonstrates what I'm trying to say. Now, spontaneous symmetry breaking is, as we all know, very important in condensed matter. It explains many observed orders. For example, crystals, magnets, superfluids, and superconductors. In fact, there's a generalized notion of symmetry and there's a generalized notion of breaking, which also accommodates other kinds of phase transitions. So it's important to ask what are the rules governing spontaneous symmetry breaking. Right? So there's a standard picture, which is we begin with some kind of a potential that dominates the partition function, which has a minimum that preserves all the symmetries. So the equilibrium state is described by the partition function, which is dominated by fluctuations about this minima, so it preserves the symmetry. But as we tune parameters, in particular temperature, to sufficiently low values, the potential can splinter, the number of minima of this potential can splinter, where each of these things don't preserve all the symmetries, but only a subset of it. And the partition function is dominated by fluctuations about one of these minima. So if you look at observables, long distance observables, you don't see the symmetry anymore, and it's spontaneously broken. And this describes some kind of an order, and we can further order the system by breaking the symmetries even further. Let's say there are some symmetries left over in this vacuum. You can spontaneously break that and then reduce the number of symmetries and increase the order and the number of vacua and so on and so forth. So this picture is quite standard and goes by the name of the Landau paradigm. But there are some constraints. Right? One thing is you see that any transition, you necessarily need to increase the number of vacua. There's no transition where the number of vacua are the same, for example. And the second one is the symmetries of one vacuum can always be identified with a subset of the symmetries of one of the other vacua. So for example, here, these two vacua have symmetries which are a subset of this one, and so on and so forth. So there are constraints in this particular picture, which goes by the name of Landau paradigm. So, conventional orders, for example, of the kind that you find in the Ising model, can be described by replacing near the critical point the system by continuum theory, where there's a potential that undergoes this kind of a transition, which describes symmetry breaking. Now, of course, in the last 20 years, there have been several examples of transitions which go beyond this particular paradigm. These have been dubbed deconfined quantum critical points in this very influential paper published about 20 years ago. The paradigmatic example of a deconfined quantum critical transition is the so-called Neal to BBS transition, valence bond solid, where neither of these two ordered states have vacua which has symmetries which are subset of the other. So for example, this thing breaks more internal symmetries than lattice, and this thing breaks more lattice symmetries than internal. So you can't identify, so in the Landau picture, there's a very nice parent-daughter kind of a hierarchy where you can say which one came first. There's an answer to the chicken and the egg problem, but here there isn't. Like you can't say which one is the parent and which one is the child. So this cannot be described by the Landau framework. And the Landau paradigm doesn't just tell you what can happen, but it tells you if you find a transition between these, what is supposed to happen. So if you find a direct transition between two Landau incompatible phases, the Landau paradigm tells you that either this is of a first order nature, it's a first order transition, or you fine tune more than one parameter. It's not a generic transition. So you tune temperature and some other value, in this case, like two different quantum parameters, fields or something like that. And it cannot be described by a continuum theory of what are called order parameters, but what this paper went out to show is that you can't write a theory purely in terms of order parameters, but there's this cool theory you can write down where there's like some multi-component matter coupled to gauge fields and so on, and you identify the phases with some kind of a Higgs or deconfined, or phases of gauge theories coupled to matter. That's deconfined quantum critical points. It's called deconfined because at the critical point, when you tune the parameters to reach criticality, the gauge fields make their appearance, whereas in either of the ordered phases, there's no gauge fields that are playing any important role. So that justifies the word deconfined. But we could ask, what are the necessary conditions for such Landau incompatible transitions? Now, one thing is clear, which is that deconfined gauge fields are not a necessary condition. So it was very early understood that gauge fields are a structure of redundancy. So if they're redundant, there are dual descriptions possibly where the gauge fields are no longer present. So there's an alternative formulation of the same transition which had gauge fields in the previous slide, which was formulated using nonlinear sigma models with topological terms and so on and so forth, where there are no gauge fields at all to be seen. So deconfined gauge fields are not really a necessary condition. It was called that way, so the name stuck. But the second word, quantum, is more important. Like you could ask whether these transitions have some kind of a necessarily quantum mechanical nature to them. And this is, in my understanding, I believe has been the consensus. So for example, there was this review article, I think, by Rajiv Singh from UC Davis, where he asks the question, does quantum mechanics play a role in critical phenomena? Right? So the answer in short is usually no, but in deconfined quantum critical transitions, the answer is yes. In fact, there's a blog article, it's called Condensed Concepts by an Australian physicist, where it's advertised as, like, the deconfined quantum critical transitions are advertised as being truly quantum. And the reason for this is quite visible if you look at the system that I was talking about. So here we have some kind of a spin-half moment, a system of spin-half moments sitting on a square lattice. And if you want to describe the equilibrium dynamics, the equilibrium properties using a partition function in the path integral formulation, you'll realize that you have to deal with the Berry phases associated with each of these spin-half moments. And if you look at the path integral formulation, these Berry phases, because of the way they're located on the lattice, produce interference effects. And these interference effects are crucial in producing these transitions. In fact, I learned all of this from Masaki's wonderful lectures when he visited ICTS a few years ago, where in practice what happens is, due to these interference effects, there are certain monopole operators that are suppressed, and it produces either a wider range of stability, or it produces transitions that you would otherwise have not been able to encounter in the presence of these monopole operators. So it's considered in this, at least in these examples, play a very important role. In fact, this is also consistent with what are called Lipschutz, Matters, Oshikawa-Hastings constraints, which tells you under what circumstances can a system, under what kinematic circumstances can a system have a trivial phase. And these Berry phases also have an alternative interpretation in terms of what are the way the symmetry is organized. It's the technical word for these are anomalous symmetries, and how the structure of configurations and defects and so on are constrained by the presence of these constraints / anomalous symmetries. And all of these are, can be at different phases of different sides of the same phenomena. I'm going to make the case that none of these are necessary. So no quantum, no deconfined gauge fields, but Landau incompatible transitions are generically possible. So I'll do this using a family of counterexamples. So this is going to be a series of, I've written a classical model, but it's actually a family of classical models where it can be shown quite easily that there exists transitions of the Landau incompatible variety. I won't call it deconfined quantum criticality anymore because this is a more appropriate term. So these models are actually not invented by us. They're quite old. They were published in 1977, about, I don't know, 47 years ago, by Jose Kadanoff, Kirkpatrick, and Nelson. And it's a very familiar system for anybody who's taken an introductory course in statistical mechanics. So the model is defined on a planar lattice. It doesn't have to have any regular structure like a square lattice or anything like that. And it has rotors. So the Hamiltonian that describes the energetics is the classical XY model, right? Which has a U1 rotation symmetry where you take each of these angular variables and rotate it by any angular quantity, and it's a symmetry. But these are deformed by adding all harmonics of perturbations that break the continuous U1 symmetry down to Q-fold rotation symmetries. So it's like it favors, the symmetries are of a clock variety. So I add all harmonics to make it generic. So in addition to this Q-fold rotation symmetry, there's also another symmetry which I'll, for convenience, call time reversal, although it's not appropriate for a classical model, where you take the variable theta and then map it to minus theta. So this prohibits the appearance of perturbations of the kind like sine theta or something like that. So these are the two symmetries, like the Q rotations and time reversal. And I'll argue that the phase diagrams for these models, so you see for each value of Q, you get a different model with different symmetries and different phase diagrams. So I'll argue that all even Q greater than 4 phase diagrams have a direct stable Landau incompatible transition between the symmetry breaking phases that are not described by the Landau paradigm. So before I do that, let me begin with Q equals 2, which is outside the series of examples, where actually the prejudices from Landau, which I described before, are validated. So I just list down the perturbation. So there's the XY model, and the leading harmonic is cos 2 theta, and the second leading harmonic is cos 4 theta. Everything else is actually not important. So I'll chart phase diagrams where I plot temperature, I vary temperature on the y-axis, and the strength of the leading coupling, the leading harmonic, gamma 1 on the x-axis. So all the phase diagram I'm going to be drawing are these two parameters that are being tuned, the temperature on the y-axis and the leading harmonic on the x-axis. The sign of gamma 2 plays an important role in what phases appear, but for the purpose of what I'm talking about, it's not very essential. So there are two symmetries here. There is a pi shift of all theta angles, and theta goes to minus theta. So that this forms a Z2 cross Z2 symmetry. So there are 4 symmetries in total. Now, the most general situation is when gamma 2 is negative. Is this thing over here. Let me begin by listing the phases. At high enough temperature, you restore all symmetry. So you get a boring, disordered phase. I'll denote as PM to stand for paramagnet. At sufficiently low temperatures, all 4 symmetries are spontaneously broken, and you have 4 vacua. I'll use this notation that the JKK and the authors also use, which is I'll use these arrowheads to point what the vacua look like. So the vacuum is, in this case, there are 2 vacua where all spins point in the 0 degrees and all spin point at 180 degrees. So there are 2 vacua. So here there are 2 where like all spins point in 90 degrees and minus 90 degrees. So I hope the notation is clear. So I'll be using this. So here you see there are 4 vacua with roughly 45 degrees angle separation. Now you see that at high temperature and low temperature, all symmetries spontaneously, low temperature also symmetries are spontaneously broken, but at intermediate temperatures you get these partial symmetry breaking phases where you have 2 vacua, and if you look at the symmetries that are left over in each vacuum, it's always going to be Z2. But these 2 phases are Landau incompatible in a very straightforward way, because I argued that if it's Landau compatible, the number of vacua have to increase. The number of ground states have to increase. So if there are 2 parts of the phase diagram with the same number of vacua, either they are Landau incompatible or they're the same phase. They're the only 2 options possible. So if there exists a direct transition between these, it would be a Landau incompatible transition. But you see that in order to have a direct transition between these 2 phases, you always have to tune 2 parameters if it's continuous. So here you see you have to tune temperature to a certain value and gamma 1 to a certain value, and you have to go through this, a multi-critical point. So of course this is consistent with Landau prejudices. Or you tune the second harmonic completely away, and then there's a generic region, but you already tuned 2 parameters. Finally, there is a stable transition between these two phases by tuning a single parameter, but that happens to be first order. So this is an example which is completely consistent with our prejudices that Landau provides for us. Right? But it turns out that this is the only case. For all other even q values, for example, for q equals 4, this point for negative gamma just extends to an entire region and produces a stable Landau incompatible transition. The universality class here, the critical theory here is that of a free Gaussian theory with continuously varying critical exponents, but it's stable in the sense that you can reach it by tuning a single parameter, and it's between two Landau incompatible phases. And how do I argue that these are Landau incompatible? You can look at these, the symmetries of each of these phases. I use this notation where the residual symmetries are always going to be of a Z2 kind, which is generated by time reversal followed by a certain number of rotations. This is going to be the residual symmetry always. And the number of rotations you have to supplement the time reversal with is denoted here. So for example, here the residual symmetry is just time reversal. Here the residual symmetry is time reversal followed by one rotation. So that's how I describe it. So here, for all even q values, you can easily see that none of these vacua have symmetries that are subset of any of these vacua, which are distinct. So these two are demonstrably Landau incompatible, and there's a direct transition between them. The transition to the high temperature disordered phase and the low temperature completely ordered phase are completely Landau compatible, and that can be understood in a fairly straightforward way. A curious thing which actually JKJN were particularly interested in is for Q greater than 6, the transition to the high temperature phase is not direct, but it's interrupted by an intermediate gapless phase rather than direct transition. Now we can understand this quite straightforward. So are there any questions about the phase diagrams? So how do we prove that this is how the phase diagrams are going to be? So we use standard tools by a process that's quite standard, devised by Villa. We can map the original lattice model of rotors and so on into this continuum model, which is a free Gaussian theory. Now, this is a conformal field theory that's perturbed by operators, so-called scaling operators. These are just inherited from the anisotropies that I use to perturb my original model. This perturbation actually appears as a regulator. If you know the Villan procedure, you'll be very familiar with it. And one could read this in the sense of renormalization group and ask whether this is relevant, irrelevant, and so on. So this regulator that appears in the continuum formulation, when it's the dominant operator, it produces the high temperature disordered phase. And everything else produces the ordered phases that you see in the phase diagram. Now, all of these operators, when they're relevant, drive the system to different kinds of phases. But it turns out that there are scaling dimensions which tells you whether they're relevant or not. Actually depends on the microscopics in a very complicated way, but they're not all independent. For example, if you take the product of the scaling dimension of the operator that produces the high temperature disordered phase with any of these operators, it actually does not depend on any of the microscopic parameters, but it's dependent on what harmonic you're looking at. So this is a constraint about the nature of the conformal field theory that describes the fixed point. And we can argue that for Q greater than 4, there exists a regime where the fixed point is perturbed by a single relevant operator. So for Q equals 4 and greater, it turns out that there exists a regime. We can't tell what it is because the mapping from the microscopic parameters like temperature and gamma 1 and so on to the scaling dimensions is very complicated, but we can prove the existence of a regime, a stable regime where there exists a single relevant operator, which when you turn it on, drives your system to either this phase or this phase depending on the sign. But if you tune that away, there are no relevant operators possible and you have a stable gapless theory, which describes the stable transition between these two phases.
So Gaussian transitions are somehow special because if I think about the BKT phase diagram, they are infinitely susceptible to anything. So does it really violate the Landau criterion?
Yes.
Because it's not a fixed point, it's a line of fixed points.
But it's still a direct transition between two incompatible phases.
I know, but
between incompatible phases.
Somehow
the fact that the conformal field theory is strange as
no, but somehow if you write it down in RG, I mean, if you add something which is a sequel to one with a SU2 symmetry, then I will agree with you immediately. Because then it's a line of fixed points, which is very well defined. But these fixed points are not stable, right?
Why are they not stable?
Because in the Gaussian, the Gaussian line in the BKT phase diagram, you put an infinitesimal perturbation and you move away from that.
I just proved that it's not true because all of these points are individual fixed points. They have exactly one relevant perturbation in this region. And if you turn on that perturbation, indeed, like it becomes one of these two phases. But along this line, they're all continuously tunable fixed points.
Okay, let me say it like this. If I put the sine-Gordon model on, if I discretize it, it is impossible to have stability of a Gaussian transition. Do you agree with this?
I don't know what those words mean because what is
sine-Gordon model?
Right.
You discretize it.
Right.
Okay. It is impossible to have a stable Gaussian point. Do you agree with this?
If the operator is irrelevant, then it is stable.
No, because whenever you regularize it with a local lattice action, this is always moving away from the critical point.
Oh, okay.
Okay, maybe we discuss this later.
Yeah.
Because if you don't agree on this, then we should discuss.
Any other questions? So, in addition to just the existence of a transition, we can also study other phenomenology, which is quite well known in the TQC community. So there's a lot of wonderful work to argue how we can understand these transitions in various different ways. So for example, one important phenomenology is the existence of an enhanced symmetry at the deconfined quantum critical transition. So for example, in this transition, if there exists such a thing, there's a formulation which takes the three-component Néel order parameter and then the two-component valence bond solid order parameter and sticks it one on top of each other to form a super order parameter. And the claim is that at a transition between these two, there's a continuous symmetry between them. So there's an enhanced SO5 rotation symmetry between these things. And in fact, many numerical studies that look for DQC transitions look for this enhanced symmetry as some kind of a smoking gun signature. So that's actually quite easy to see here. So we can ask what are the order parameters for these two partial symmetry breaking Landau incompatible phases. It turns out they're very simple to write down. It's one of them, for this guy, it's sine q theta over 2. For even q, this is a perfectly varied local operator. And for this guy, it's cos q theta over 2. And we can show that these have the right kind of symmetry transformations to be order parameters for these phases. Now, if you line these two order parameters into a two-component object, we recognize this immediately as a unit vector, which is exactly the order parameter for the quasi-long range order for the XY model. So this emergent symmetry is quite naked to see in this model, which is slightly more obscure in the more complicated examples. Finally, there's another feature, which is how do we understand the transition in terms of defect proliferation? Now, let me remind you that in general phase transition, we can think about something being condensed or proliferated as driving the transition. For example, typically when we are in a disordered phase and we want to move to ordered phase, there's some kind of a charge that you condense to produce the ordered phase. Whereas if you're in the ordered phase, you typically look for some kind of a defect, for example, cracks in a solid or something like that, and you make them, you proliferate them, you go to the disordered phase. Now, typically, like for example, the Ising model, the defects look like this, like there are domain walls between two vacua. And in usual circumstances, these domain walls, these defects are charge neutral. So when you condense these charge neutral defects, then you restore all symmetries. That's what happens. Since they're not charged, you proliferate them, it's completely invariant under all symmetries and you restore them. If you look at, for example, the valence bond solid order and then try to create a defect between these four different ground states, it's very easy to see that it always exposes the spin half moment. So typically what happens is, for deconfined quantum criticality, when you start with one ordered phase and look at the defects, it traps some kind of a charge in its core or something like that, and when you condense that, you restore one symmetry but break another. So it's a very nice picture to understand how the restoration of one symmetry produces the breaking of another. Now, we can see that also very easily in this model. So let's start with one of these partially symmetry breaking phases and look at two vacua, like some kind of an interpolation between these two vacua. So here, all spins are pointing at 0 degrees. Here, all spins are pointing at 180 degrees. And they have the residual symmetry of these two vacua is just time reversal, it's T. So if I create a smooth domain wall, where I start with this vacuum where all of them are pointing at 180 degrees and then interpolate it to all spins pointing at 0 degrees, you realize that if you hit this with a time reversal transformation, on both ends, where you have the vacua, the system is completely invariant. Like this maps to the same thing, this maps to the same thing. However, at the core over here, which has some finite length scale deep in the face, this transforms. So what this is telling you is that domain walls in one of these phases traps the symmetry, in fact, which produces symmetry breaking of the other. So when you melt these domain walls and approach the critical point, this correlation length where these domain walls are trapped diverges, and then you have a soup of charged objects, which is why you have breaking of one symmetry and restoring of the other. Right? In fact, there are more things you can understand which is not available to us in the conventional DQC model. So for example, if you start off with this model, there's actually three kinds of defects that we can write down. One is you sit in the vacuum and flip just one of the spins, and that's a charge defect because there's a charged particle, you activate on symmetries and then this transforms. Now, if you condense these charges, you actually produce the Landau compatible transitions that are seen here. You start from here or here, condense the charges, you produce these transitions. In fact, I wrote down this smooth interpolation, but I didn't need to do that. I could just do a hard interpolation of this kind. Right? So I have all vacua here and all vacua here, and this is completely invariant under all symmetries. This is a neutral defect. So instead of condensing these things, I could condense this, and in fact, what that does is restore all symmetries, as you would expect. So there are neutral defects and there are charged particles, and condensing the neutral defects restores all symmetries in the way you would expect it. Condensing all charged defects breaks symmetries as you would expect, but you bind these charges to these domain walls, and this can happen completely energetically. Like, energetics might just favor, instead of this being the lightest excitation or this being the lightest excitation, it could just have some kind of an effective attraction which binds these charges to the domain walls, and it would soften these hard domain walls. And if you melt these by tuning gamma 1 at some intermediate temperature, you would restore symmetries and break another. So all three are completely possible. Now, it turns out that in the kind of DQC models that I showed, like things of this kind, linearly BBS, these independent charges at domain walls don't appear. And this is actually an interesting thing as to why they don't. So there's a review by Senthil a year or so, I think earlier this year, where he argues that if you look at what kind of configurations appear in your NIL, like in your partition function, the nature of symmetries, this interference effect that I described, ensures that there are no defects without symmetry charges. So these charges and defects don't have independent existence, but they only have existence when combined. All other independent configurations are removed from the partition function by destructive interference. And this has to do with this anomalous symmetry. Like, this is another way of thinking about anomalies, which is, as he says, binds charges of one to the defects of the other. And this is an important fact. So in this kind of systems which are constrained by Lieb-Schultz-Mattisch or Ishikawa-Hastings constraints, you can't have defects without charges in them. But in our model, you perfectly well can. All you need is the right kind of energetics. Right. So for the LSMH-OH condition, there's a mixed anomaly between internal rotation symmetries and lattice symmetries. Another place where such kind of DQC transitions appear is boundary of SPT phases. If you don't know what they are, happy to tell about them. But in this case, there's none of these two cases, and you can have perfectly stable conditions. I'll just skip this. Now, you might wonder, so I've exclusively focused on even Q phase diagrams. It turns out that we can also analyze odd Q phase diagrams where there's an additional surprise. So if you look at the phase diagrams that are drawn, you have the same structure. You have all symmetries restored at high temperatures, all symmetries broken at low temperatures, and partial symmetry breaking at intermediate temperatures, and a stable transition between them. But I claim this is not a Landau incompatible transition. It turns out that if you look at the residual symmetries of the vacua here and the vacua here, they're exactly the same. So if you see here, the 0 degrees vacuum has the same symmetry as the 180 degrees vacuum. 120 degrees vacuum has the same symmetries as minus 120 degrees, and so on and so forth. So it turns out that these vacua and these vacua have the exact same kinds of symmetries. In fact, I argue that they both belong to the same phase. So there is a stable transition or a stable critical line at the very least in what seemingly seems to be a single phase of matter. And in fact, if you look at the order parameter, this is the exact same order parameter that detects these two phases, these two regions of the phase diagram. It just causes q minus 1 theta over 2. When q is odd, this is a valid local operator. So this is what I think is a first example of a classical version of what is called an unnecessary critical line. And the claim is, I don't know what it is in this phase diagram or in this model, but there exists perturbations such that you can connect this phase all the way to this phase, and this stable critical line has to terminate at some point. So there's parametric stability in the region that I've explored over here, but there exists some perturbations which I won't be able to tell you at the moment, where this can be connected. In fact, the easiest way to see this is Q equals 1, where it turns out that the partial symmetry breaking phases are smoothly connected to the paramagnetic phase. So if you see over here, all spins are pointing to the right, all spins are pointing to the left. They appear to be distinct phases, but you can actually circumvent, you can go all the way around through the paramagnetic phase and then connect it to the other. So I'm guessing that for the other odd Q phase diagram, this unnecessary critical line terminates in some kind of similar way. Like I said, this is very reminiscent of what happens in liquid gas, where you have a seeming transition between liquid and gas, which abruptly terminates. But the important thing here is the liquid gas transition is of a first order kind. And in fact, this is used as a moral lesson to say, don't take first order transitions seriously because they can terminate, they're very fickle, and you might be exploring two sides of the same phase. But it's generally assumed that second order transition, continuous transitions cannot abruptly terminate. And of course, this paper by Zenby and Senthil a few years ago made the case using a field theory argument that such transition should be possible. And in fact, in a letter last year, Sid Parameshwaran, Michele Fava, and I produced this diagram where you do have a abruptly terminating critical surface in a quantum mechanical 1+1 dimension model. But there are many examples by now, and all of them are quantum mechanical and in some kind of a topological setting. But here is unnecessary critical transition within a completely classical model. So just as a parenthetic remark, there are quantum models which have the same kind of phase diagram. These are perturbed XXZ Hamiltonians with some kind of anisotropies. They have the exact same phase diagram, but this is less surprising than classical model. But indeed, all of these are completely anomaly free. And in fact, has some other rich possibilities. They can have like topological phases in their phase diagram. The basic point that there exists stable Landau incompatible transitions remains. We were originally interested in understanding some technical thing about whether you need anomalies to have these deconfined quantum critical transitions, but that's why we were exploring these models, but we found classical models which had a broader point to make, and I focused mainly on that. So with that, I'll end my talk. In summary, there are these Landau incompatible transitions, such as symmetry incompatible transitions, or transitions between in the middle of the single phase, which are seemingly less special than previously imagined. Like the conditions required for their existence are less special than what we thought previously. Now, the practical context in which many of these examples, DQC and so on, have been studied are frustrated magnets, quantum magnetism, and in higher dimensions, and it'll be interesting to see whether they have any kind of implications, like maybe it opens up larger set of experimental possibilities to study DQC in settings that we previously might have not considered. Another remark is that unnecessary criticality is accompanied by boundary phenomena. So even in this classical model, I believe that there are interesting boundary phenomena, surface critical behaviors lurking in its in these models, which I have to explore. Finally, it'll be interesting to ask the question about what other, in quotes, quantum phenomena could potentially be seen in classical statistical mechanical models. For example, there are many topological phases which we believe are intrinsically quantum. There's no solid reason to believe that, and it'll be interesting to see if there are classical models that can just realize these things. So with that, I finish, and then if you have any questions, I'll be happy to answer them.
So this is regarding presumably the second point. Are there three-dimensional classical models known which show similar properties like classical analogs of this TQCP?
Not that I know of, but I strongly believe there should be.
Okay, would you elaborate on that? Because I thought that the fractionalization in one dimension, if I think about the quantum counterparts, is a different mechanism from the kind of fractionalization that we know in higher dimension. And that's why I would think that having these kind of classical systems in higher dimensions would be more difficult.
All my models, there is no fractionalization whatsoever.
No, of course.
My belief is, like, the way I see this happening is we have to find out conditions for charge defect binding. So if the energetics of a model, like we have to study, like, go to an ordered phase and then study when do charges and defects get bound together. And that's more stable than independent charges or defects. So if you can find a stable regime where that can happen, and condensing this composite object should produce a stable Landau incompatible transition. So in quantum mechanical settings, fractionalization and all of that are nice ways to understand this, but classically, I would think that's how I would look.
Yeah, so I have a question regarding this phase diagram. I think I didn't follow some of the things. So, yeah, over there. So you said that, so at some point below, right, there is a, so between these ordered phases and the easing, you have a first order transition.
Sorry,
Below and above, yes?
So these are all continuous transition with Ising universality class.
And what about the one on top? Between PM, the paramagnet and the...
Right, so here there's a very nice story using something called multi-frequency sine-Gordon model, where you can show that for Q equals 3, you get the 3-state Potts model. Q equals 2, you get, so here is the 3-state Potts model. Let me show you the other phase diagrams. Yeah, so for Q equals 2, you can show that these are Ising transitions. And for Q equals 4, this is Ashkin-Teller. So it's the or before conformal field theory. Whereas here, there's a stable region, there's no relevant operators. So all of these are continuous. For gamma 2, the second harmonic being positive, there's, I don't remember this, but I think there's a first order transition that appears at very low temperatures.
I see.
But this phase diagram that I showed for simplicity, everything is continuous. Everything is second order.
Okay, thanks.
So where the critical line it ends, that is like for it's a critical point, right?
In unnecessary critical.
Not here. Yeah. So usually when you have say liquid gas transition at the critical point, it's like a second order.
Yeah.
Right. So here, do you see some kind of analog where the line ends for the odd Q case?
In the odd case, we don't know what parameters you have to tune to connect them. So we don't know how it ends.
Oh, but
so I have a field theory way of understanding how it ends, but I don't know what microscopics leads to that. These are easier in quantum. So the technical reason is what you need to add is a disorder operator, something called a disorder parameter. And those things are not naturally, you can't add them in the classical model. Quantum mechanical models, you can do this easily. So we don't know how to terminate it in this model.
Okay.
But in the example that we had in a different paper, I can tell you what happens with the end. So here you see the stable line that ends by, there's a different universality class. This is a stable conformal field theory with central charge 1. There's this point with central charge 3/2. There's abrupt change in universality class, and then you have these two balloons. So this is how it ends. The critical point in the liquid gas transition is replaced by these balloons. In fact, there's another model by Paul Fendley and company, which they never published yet, but they also say they see this balloon structure, so maybe that's generic.
What do these balloons mean? Sorry?
They're gapless phases.
Okay.
So the line terminates and then just balloons out into an stable phase.
Thank you for, very interesting presentation. So, if I understand correctly, in 1D quantum spin chain context, I think examples of this non-Landau type criticality has been known between Nail phase and Diamond phase, and so on. So, and they can be described in terms of effective, double sine-Gordon type theory. So, in that sense, as you presented, if you have some classical system,
yes,
which is described by the same sine-Gordon, I think it's kind of natural to expect this kind of transition. But in higher dimension, it's a bit more, roughly speaking, difficult to realize non-Landau type transition in my understanding too. So do you have any idea or insight into the classical version of this non-Landau transition in higher dimensions?
So let me begin by making a point about the 1D quantum models. So it usually is described effectively by some multi-frequency sine-Gordon model. But you'll see that in all these models, every one that's been published so far, they're anomalous in the sense that the leading harmonic was always suppressed. So it's like cos 2 theta, cos 4 theta, and so on. So it's distinct from the model we have, because here you have this leading operator which produces the high temperature phase that produces a unique ground state. So this has to do with this LSMOH / anomaly business. Okay. So those quantum models, even though they map onto the effective field theory, it's similar but not the same. On the other hand, like the higher dimensions, what we lack is the concept of this conformal manifold. They appear in very rare circumstances. So this continuously tuning critical exponents, which really helped us a lot, is not available. But my sense is what I'll probably repeat the answer I gave Subhro, which is The way I would go looking for Landau incompatible transitions in 3D classical systems is to find out energetic conditions, look for energetic conditions which binds charges to defects. So if you have like some kind of a defect and a charge that naturally can bind together, produce energetic conditions such that they bind, and once they do, when they condense, all they can do is produce a Landau incompatible transitions. So starting from the conformal field theory point in higher dimensions is of course a very difficult thing, even for like practitioners of the field. I think we should play to our strengths and look for energetics of binding.
Thank you.
If there are no other questions, let's thank the speaker once more.